Hi, I'm Solomon Stevenson.
And I'm Doug Jones.
And we're here today for an exciting series of interviews we have lined up with some famous astronomers, Kepler, Newton, Copernicus, Brahe, and Eratosthenes.
We're excited to ask them about their lives and their work for a great educational experience for all of you.
Without further ado, here is Copernicus.
Mr. Copernicus, it's great to have you here.
Oh, please call me Nicholas. I'm happy to be here to talk about my discoveries. As you may know, I was reluctant to discuss them for a long time for fear of backlash, but I'm glad I can come and spread the knowledge now.
Me as well. So Nicholas, tell me about your childhood and your education.
Well, I was born in a small city in Poland in 1473, son of a merchant and the youngest of 4 children. And I had a good childhood, but my father unfortunately died when I was very young, and I was taken under the wing of my uncle, Lucas Watson Road. I attended a couple of schools under his recommendation and arrangement until it came time for me to attend University of Krakow, where I attained my foundation of mathematical and astronomical knowledge, studying in the Department of the Arts. It's where I first began to really question the then accepted ideas of astronomy created by Aristotle and Ptolemy. And after a stretch of studying law at the University of Bologna in Italy, I returned to my astronomical studies in Italy as a disciple of the great astronomer Domenico Maria Novara da Ferrara. I dedicated much of the rest of my life to the study of the stars.
Wow. I understand that you took issue with Ptolemy's theories to explain retrograde motion specifically. Could you explain a little bit more about that?
Yeah, well, firstly, the Ptolemaic model was exposing itself to be flawed even by normal observation during my time. It was hailed as good at predicting the positions of the planets. However, as time went on, the predictions it made got less precise and less accurate. And further, his model overcomplicated retrograde motion. His model, which was a geocentric model, of course, in order to be accepted, it required that each planet had very large epicycles at all times. And if these epicycles weren't present, then one could not accept his model because the retrograde motion of the planets that we had observed.
So how did you improve upon this? And you said your big problem was how complicated it was. How did you end up simplifying it?
Well, so my model, which was the main difference, was that it was a heliocentric model, meaning that it placed the sun at the center of the universe rather than the Earth. And my model, I believe, was superior because it required much less in terms of the epicycles and explained retrograde motion simply by the nature of the adjacent orbits of the planets, both with motion in the same direction of the orbit. I believe the simplification of my model is accurate and an easier idea to accept. It fits better with the data regarding planetary position and retrograde motion with a simpler explanation. I had to look over 1,500 years of data following Ptolemy's time to support my theories, but the observational data does support them.
Amazing. At some point, you condensed your findings into a book that was called On the Revolution of Celestial Fears. This book was created using using years of observational data and analysis and synthesis. Would you like to talk about that a little bit?
Yes, yeah. So I consider that book my greatest accomplishment. I only waited until my later years to publish it for, as I've already mentioned, fear of the controversy given the powerful religious leaders during the time who accepted the geocentric model. It is the first part, in the first part of my book, in a chapter titled, Can Several Motions Be Attributed to the Earth, the Center of the Universe? It's in this chapter that I state that the Earth is not the center of all the revolutions. This is indicated by the planet's non-uniform motion and their varying distances from Earth. I go on to explain that I believe that there's not one true unmoving center of the universe, but that the sun resides somewhere near a general center. Further, I also hypothesized that the Earth partakes in the same type of motion around the sun as all the other planets, and this motion causes the retrograde effect, which we see.
That's amazing. Your work truly revolutionized the way scientists have seen and continue to see the universe. Thank you for your contributions to the field, Nicholas.
Thank you. Yes, it's good to be here today.
Go.
Now we are truly honored today to be talking to Isaac Newton. You may know him from his work in motion and physics and is one of the most notable physicists in history.
Pleasure's all mine. I'm always happy to talk about my work.
Let's start with talking about the famous apple myth. Is there any truth to this story, or is it just a tale that people tell?
There's definitely a degree of truth to the story. I did, in fact, see an apple fall from a tree, and that was instrumental to me developing my theories and inquiries into the phenomenon of gravitation. Seeing that the apple fell straight down instead of at an angle perplexed me and drove me to want to understand the science behind what happened. What my research ended up discovering was that every particle attracts every other particle in a way that is directly proportional to their masses, but also inversely proportional to their distance from each other. This is the fundamental idea of gravitation that we still use to this day. What is purely myth about that story, however, is this admittedly cartoonish interpretation that the apple somehow fell on my head and hit me, and then that struck me with the idea. That is complete fiction.
How interesting. It's hard to imagine what astronomy would look like without your work in gravity. But that's not the only thing you're known for, is it? In the same book where you discuss gravity, you also wrote your famous 3 laws of motion, correct?
I did. It's Philosophiae Naturalis Principia Mathematica. It's really my magnum opus and has many of the biggest contributions, of my biggest contributions to the field contained in it. There are the 3 laws of motion, of course, which is probably the biggest contribution within, which is, let me make sure I get the exact wording right here. 1, that every body preserves in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. 2, that the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. And finally, 3, that to every action there is always opposed and equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed to contrary parts.
Wow. I don't think I had ever heard the original wording before. What other breakthroughs did you develop through the making of Principia?
Well, astronomers will note that a lot of modern understanding of orbits is actually based upon my research there. In fact, prior to publishing the Principia, I wrote a letter to a friend known as De Mutu Corporum Ingerum, in which which ended up being published in Principia anyways. But in that letter, I sort of put gravity in terms of centripetal force, and that's pretty instrumental to understanding orbits and how they work in relation to gravity. My research wasn't only on physics either, though. A lot of modern understanding of light wouldn't exist without my work in that sphere.
That's interesting. What did you uncover in your work on light?
So before my time, the notion existed that light is homogeneous and in its purest form is white, and that when color happens as a phenomenon, that's only modifications of pure white light. What my work showed is that the current model of light is much more complex than the one of the past. In my model, in which I developed in my groundbreaking paper, Optics, I showed that white light is in fact the combination of every colored light, and that the light from the sun is all the primary colors mixed in proportion. I figured this out in a series of experiments that utilized a prism to refract sunlight. Light is in fact heterogeneous, not homogeneous.
That seems so fundamental. Did your experiments with light lead to any other results?
They did, in fact. I built what is now referred to as the Newtonian telescope, named after yours truly, for these experiments. It has a relatively simple design consisting of 2 mirrors that reflect light to the observer.
That's amazing. Clearly you've had a diverse and fruitful career.
I would definitely agree with that.
Well, thank you for your time, Mr. Newton, but that's all the time we have for you today.
Thank you.
Hi, I'm Doug Jones, and I'm here with Tycho Brahe, an accomplished astronomer. He's here to talk about his discoveries in the field.
Thanks, Doug.
So to start off, how'd you become an astronomer, Mr. Brahe?
Well, I was a young boy, only 13 at the time, and I saw my first solar eclipse. I had heard secondhand several days before and was astonished that such a magnificent feat could be predicted. It struck me as something divine that men should know the motion of the stars so accurately that they were able a long time beforehand to predict their places and relative positions.
That's amazing. Can you tell me about how you make your observations when you're practicing astronomy?
Great question. I have my own observatory, and there's a particular spot where I can sit at night and measure the positions of the heavens through a large rectangular hole in the wall and make exact measurements with an elongated protractor.
Can you tell me some more specifics about the observations that you've made in your observatory?
Sure, Doug. I watch the planets diligently, keeping track of their motion at all points in the sky. In 1572, a year after building my observatory, I watched the birth of a new star, a miraculous moment for both me and the scientific community, who had thought previously that the sky was unchangeable. Several years later, I saw a comet in the northern sky and managed to prove that it was beyond the moon rather than in our own atmosphere, an idea unheard of at the time.
That really is fascinating. And I know that you've had a personal relationship with Johannes Kepler, who is also part of this interview series. Can you tell me a little bit more about him, if you have any information?
Well, unfortunately, I hired him shortly before I passed
I
away,
see.
so I can't say much. He didn't have much training in the field of astronomy, but he liked the pay.
All right, I suppose that's good enough. Thank you very much for your time.
Thank you. Mr. Eratosthenes, thank you for taking the time to talk with us today.
It's great to be here.
So, to start off, could you tell us a little about how you first got interested in the geographical and astronomical research you carried out during your career?
Well, I was always a student of mathematics and science, beginning with my continued studies in Athens, which is also where I wrote and published my first scholarly works.
In your famous work of Cleomedes on the circular motions of celestial bodies, Cleomedes credits you with being the first mathematician to accurately measure the circumference of the Earth. This measurement, one that still stands to a degree of accuracy today, was useful in countless calculations of astronomical phenomena. How were you able to find this measurement so well?
Well, so this was, it was probably one of the most complicated things I did, but I did this by knowing that the sun was directly overhead at noon on the summer solstice in Syene, Egypt. And by then measuring the angle of elevation of the sun at the same time in Alexandria, I had these two measurements of the different angles of elevation. Once I had these two measurements, I had two angles of this triangle, and I also had one side knowing the distance between Syene and Alexandria, and I just used basic geometry and extend to find the distances that I was looking for, and I only had to extend this distance to the range of an entire 360 degrees rather than just the 7-degree difference in the sun's angle of elevation between Alexandria and Syene.
Fascinating. You must know that because of all your discoveries about the Earth and its geography, some have termed you the father of geography.
Well, yes, the work that I'm actually most proud of my publications is my 3-volume masterpiece, Geography, in which I mapped the known world into 5 zones: 2 freezing zones around the poles, 2 temperate zones, and 1 warmer zone around the equator and the tropics. Further, I'm also proud of my work with calendars and my theory of the leap year and the calendar year.
Now, that is very interesting. What led you to the conclusion you made about the calendar year?
So for that, I utilized the theories and predictions that I had calculated about the Earth's ecliptic, and how the sun seems to follow a predictable path over a predictable time.
Oh, interesting. Unfortunately, that's all the time we have, but thank you so much for talking with us today.
It's been a pleasure.
Hi, Doug Jones here again. This is another installment of our famous astronomer series. We're here now with Johannes Kepler, who is a renowned astronomer. How are you feeling today?
Good. I'm feeling good.
I'm glad to hear it. What can you tell me about your self-confession to larceny when you admitted stealing Tycho's observational data? Specifically, you said, "I confess that when Tycho died, I quickly took advantage of the absence, or lack of circumspection of the heirs, by taking the observations under my care, or perhaps usurping them."
I don't feel guilty, if that's what you're asking me. It would have helped no one to keep his observations a secret. I spent 9 years of my life pouring through his data, and was able to teach the world so much because of it. I found issues between observations he made and my own observations, and my interpretation of these discrepancies laid the foundation for my 3 laws of planetary motion. Planetary motion is not circular, it is in fact elliptical, with the sun at a focus. Second, during their orbits, planets go around equal areas in equal times. Finally, the square of the times to complete one orbit are proportional to the cubes of the average distances from the sun. Happy?
I suppose so. I had more questions, but thank you for your time. That's all we have from Mr. Kepler. Thank you.
Thank you for tuning in to Time Machine Interviews. I'm your host, Doug Jones, signing off on behalf of myself and Solomon Stevenson. We hope you find this an educational experience.